Today we're going to graph cardioids and limacons. First, we're going to learn how to graph r equals 2 plus 2 sine theta, and we're going to use y equals 2 plus 2 sine x in order to figure that out. So what we'll notice is that there's a correspondence between x and theta and between y and r. So hopefully we know how to graph y equals 2 plus 2 sine x. And then if we take a look at these 5 major points, we can map them so that r theta is where r equals y and theta is equal to x. And so what we can do is we can plot these points here on this polar axis. So the point 2, 0 would be here. The point 4 pi halves would be here. The point 2 pi would be here. 0, 3 pi halves, well, anytime r is 0, it's at the pole. Then 2 pi, we're back to r equals 2. Then we can look at some other things just to get a better idea of what is happening. Now if we plug pi fourths into this equation, sine of pi fourths is root 2 over 2, so we would see 2 plus root 2. And likewise for substituting in 3 pi fourths, 5 pi fourths, and 7 pi fourths. So we end up getting a little bit better sketch of this. So at pi fourths, we end up with 2 plus root 2, which is about 3.4, somewhere around there. The same thing happens at 3 pi fourths. At 5 pi fourths, we end up with something between 0 and 1, so it's going to be a pretty small number. And likewise at 7 pi fourths. So what we see is we see a graph that what we have to make sure that we do is we substitute these values in and trace it along this pattern where we continue to move as theta moves. So we sweep from 0 all the way to 2 pi. So it's going to look something like this, where it's kind of circular and then bounces in like that. So it ends up looking kind of like a circular looking heart, which is why we call these cardioids. It kind of looks like a heart. Now, one thing to notice is that once we hit 2 pi, if we continued, this graph would look identical, so we don't need to go any further. We would just keep tracing over exactly where we had already traced. So the period of this polar graph is 2 pi. There are no negative r values in this polar graph, and that makes sense because there were no negative y values in the original graph. The lowest value was at 3 pi halves, 0. So there was no need to go into the negatives. Now, there are no negatives in cardioids, but when we get to limacons, we might see some negatives. So we're going to do these relatively quickly. If I substitute in 0, pi halves, pi, 3 pi halves, and 2 pi, I end up seeing something about this cosine, 3 minus 3 cosine graph, 0, 0, pi halves 3, 0, 0, 3 pi halves, 6 pi, 3, 3 pi halves, and back to 0, 2 pi. Then I could look at these where I plug in pi fourths, and in the interest of saving time, I'm not going to go through how they all work, but suffice it to say, cosine of theta, when theta is pi over 4, is root 2 over 2, or negative root 2 over 2 at 3 pi fourths, 5 pi fourths. And so that'll be something that I'm just going to assume the rest of the video in the interest of time. So if I have 3 minus 1.5 times root 2 is about 1.4, so this is going to be about 2.25. So this is going to be smaller than 1 when I'm at pi fourths. It's going to be about 5, a little bit bigger than 5, somewhere between 5 and 6 when we're at 3 pi fourths. Likewise, at 5 pi fourths, it's going to be somewhere around here, a little bit bigger than 5. And when we're at 7 pi fourths, it's again back to a pretty small number. So if I trace this, I'm going to end up with something that looks kind of circular, and then back into something that looks kind of like a heart over here. So that's another cardioid. We'll do one more quick example. So here are all of the numerical values. Then I plot 1, 0, 0, pi halves, 1, pi, 2, 3 pi halves, and then back to 1, 2 pi. Now if I wanted to plot these points, I could. These are pretty small. And then these are 1.7-ish, so not quite at 2, but pretty close. So my graph, again, sweeping from 0 all the way to 2 pi is going to look something like that. Again, the period of cardioids is 2 pi, because once I get to here, if I kept going, I would just cycle over and just repeat myself, and it would just keep going and going and going. All right, now Limacons with a loop, if we look at r equals 1 plus 2 cosine theta, we have another graph that if we do y equals 1 plus 2 cosine x, we can see a relationship with x and theta and y and r. So again, we're going to do this table of values. And what we see is I end up with a negative r value. So that's going to cause us a little bit of difference in terms of what's happening. So 3, 0, 1, pi halves. Then I end up with negative 1, pi. So basically what that means, remember if we have negative r values, that goes to the opposite side. So negative 1, pi is actually going to be at the exact same point as 1, 0. Then we have 1, 3 pi halves. And so maybe in order to see what this looks like, we need to get a better look at these pi fourths intervals. So 1 plus root 2, somewhere around 2.4. So that'll be somewhere over here. Then at 1 minus root 2, that's going to be at negative 0.4, somewhere around there, negative 0.6. So if we look at 3 pi fourths, if it's negative, it has to be somewhere over here. Likewise, 5 pi fourths, negative 5 pi fourths is going to put us somewhere over here. And so what I need to do is I need to remember that as I sweep, I have to go in order with the theta values. So as I do that, I also forgot to plot this 7 pi fourths angle. So it's like 2.4, 7 pi over 4. So now what I'm going to do is I'm going to trace this. If I start at 3, 0, I go to 1 plus root 2, pi fourths, pi halves, 1. That's not that smooth, but it needs to be smooth. Then what happens is my next number is negative. So all three of these numbers are negative. So what that means is at some point, I have to cross the pole. So I have to cross the pole, and then I hit 1 minus root 2, 3 pi fourths. So notice that that's going to be over in the 7 pi fourths area. Then I sweep through negative 1 comma pi, 1 minus root 2 comma 5 pi fourths, and then my next number is positive again, so I have to, again, go back, cross the pole, and my graph will look something like this. So notice that I crossed the pole twice in this direction, and then I ended up back over here. Again, the period of this is going to be 2 pi, because once I get back here, I would just keep repeating the same cycle that I already saw. Also notice that there were negative r values here, and it's from 2 pi thirds to 4 pi thirds. Now I know it doesn't explicitly say that here, but notice that 2 pi thirds is somewhere between pi halves and 3 pi fourths, and 4 pi thirds is here. Now why might that make sense? Well, let's look at the original graph that we had, and notice that between 2 pi thirds and 4 pi thirds, our original graph was negative. So it would make sense that our r values would be negative in that region. And here's another example of it. Okay, quickly, we're going to do 2 more examples. So if we look at 2 more Limacons, I see 2 comma 0. I see 2 minus 3 root 2 halves, which is going to be a negative number. So at pi fourths, I've already gone into the negatives. So it's going to be about negative 0.4-ish or so. Negative 1 comma pi halves is going to be at 1 comma 3 pi halves. It's going to be at the same point. Then I keep mirroring. At pi, I'm now at 2. And then 2 plus somewhere around 2.2. So that's going to be about 4 point something. Then 5. And then 4 point something again. So my graph will look something like this, where I start here, I have to sweep under, sweep back, and then it looks kind of circly over here. So that's my Limacon. Again, the period is 2 pi because it would just keep repeating. Also notice my negative numbers are in here, so that means somewhere between 0 and pi over 4, I have to cross the pole. Then I have to cross the pole again in order to get back to pi being a positive number. Another one, 1 minus 4 cosine theta. Here are my r theta values. So one more time, just a reminder, I write points as r comma theta. So I would write the points like this if I wanted to write them. So this starts in the negatives. So negative 3 comma 0 is actually going to put me at the same spot as 3 comma pi. Then I'm going to skip these just in the interest of time here. So I then go to pi halves comma 1, pi comma 5. I'm sorry, 5 comma pi. I wrote it and then I said it wrong again. 1 comma 3 pi halves, and then all the way back to negative 3 comma 2 pi. So if I start here and I have to get to pi halves 1, that means that I have to cross the pole in order to get to the positive numbers. And then I'm going to end up with a graph that looks something like this. So there's my graph. Again, the period, 2 pi. Finally, another Limacon, this one with a dimple. So if I graph 3 minus 2 cosine x, I see this graph. I'm going to make a table of values again. Now notice that none of these values will be negative, and that makes sense because none of these values were negative. So we will quickly graph this, 1 comma 0, 3 minus root 2 is going to be somewhere around 1.6. Pi halves, we're at 3. 3 pi fourths, we're at somewhere around 4.4. Pi 5, so again, 5 pi. That's terrible handwriting. Well, that's actually not my fault. That's the tablet's fault. Then it's back to 5 pi fourths. We're at somewhere a little bit above 4. 3 pi halves, we're at 3. And then at 7 pi fourths, we're at about the same spot we were at pi fourths. So this is supposed to be circly looking. So it looks kind of like a cardioid but doesn't go all the way in. This is called a limacone with a dimple, because it's just a little itty bitty dimple here. And once again, the period is 2 pi, because if I kept going here, it would give me the exact same pattern as this. Okay, now 2 more really quick examples. 3 plus sine theta is going to look like this, and in the interest of time, I'm going to skip all the pi fourths situations. So 3 comma 0, 4 comma pi halves, 3 comma pi, and 2 comma 3 pi halves, and then we make our way back. So if I mimic this, it'll look something like this. I probably went a little too wide up here, as it should be circly in nature. But it should look something like that. My dimple is right here. Then 5 minus 2 sine. Again, the period of this one will be 2 pi because it repeats itself here. 0 and 2 pi for the angles. So I start at 5 comma 0, 3 comma pi halves, 5 comma pi, and 7 comma 3 pi halves, which is way down here somewhere. Oh, this is 6, so I guess it's not as far down as I'm claiming it is. So 7 would be about here. So there's this little dimple, and then it should look circly. I'm not doing a very good job of making a circle, but that's how it looks like. So once again, the period is 2 pi. Now let's go back and summarize things real fast. One thing we may want to notice is that when we had 2 plus 2 sine, notice that the cardioid heart opened up, so the big part was up. Negative 3 cosine, the big part was to the left. And that makes sense because cosine is typically associated with x, and if it's negative, it's probably going to open to the left. This sine, positive sine, opens up. Negative sine probably opens down. Now I have limacones. I have this plus 2 cosine. Notice that it opens to the right. Minus 3 sine, the big part opens down. Minus 4 cosine, the big part opens to the left. 3 minus 2 cosine opens to the left. Plus sine, the big part opens up. Minus 2 sine, the big part opens down. So that's just stuff to keep in mind. A lot of that probably makes some sense. Okay, let's recap. Cardioids, limacones with a loop and limacones with a dimple, all had these types of equations, one thing you may want to notice is that the cardioids had the same number as the plus or minus and the same number that's multiplied by the sine or cosine, whereas Limacones had different numbers. So if you go back and check, you see that all of these numbers had the same number on both parts, and all these numbers were different numbers. If I had a limacone with a loop, what I may have noticed is that this number was the bigger number, whereas a limacone with a dimple had this number as the bigger number. One more thing to keep in mind is that all of these things had period 2 pi. So that may be something that you want to recognize. That'll come in handy later when we start learning some more things. Here are some more properties that you may notice, and you can go back and check to see if all of these things make sense with the picture. But the distance to the end of the heart was the absolute value of 2 times this number, and the distance to the edge of the heart was just the absolute value of that number. So if I look, notice the distance to the end here is 4. The distance to the edge was 2. And that makes sense because A was 2. And I lost all these things. That's sad. So I guess I can't scroll around. Now when we're dealing with limacones, what we have is, if the B is bigger, we have an inner loop, and if the A is bigger, we have a dimple. But I already told you that. Notice that if the sign between them is negative, the loop goes to the left, or the long part goes to the left, or it goes down, depending on whether it's a sine or a cosine. If the sign in between is positive, notice that the loop or the long part, like the major part of it, goes right or up, depending on if it's a cosine or a sine. Then you can look at these distances and then compare them to what we saw in these things. So the distance to the inner loop is the absolute value of B minus the absolute value of A, and that's to the inner loop or the cusp, depending on what it is, and the distance to the outer loop is just adding them together. So if we go back, 3 plus 1 is 4, 3 minus 1 is 2, 5 plus 2 is 7, 5 minus 2 is 3. So notice those things show up. Then in these problems, 3 minus 2 is 1, so notice that's there, and 3 plus 2 is 5. 4 plus 1 is 5, and 4 minus 1 is 3. So notice these things are showing up in all of these places.